Is it 313?
Yep.
That's what I thought. Badgley 313. Okay, Badgley Hall 313. Okay, this is almost where we stopped last time. We're looking at the formation of ionic bonds. Excuse me. One of the rules that you follow here is always to try and fill shells. That's something that's going to happen every time we're forming chemical bonds between atoms. You're always trying to fill up shells. So the question to ask with forming an ionic bond is, what's the easiest way to have a filled shell? The easiest way in this case with sodium and chlorine is to steal an electron away from sodium and donate it to chlorine. That way both of them have filled outermost shells. Okay? So always think of that. By the way, please turn off your cell phones. There's nothing that annoys me more than having a cell phone go off in my classroom. Okay? So make sure you turn those things off before you come in. Same thing with a concert. You ever been at a concert and somebody's cell phone goes off in the middle of it? Really annoying. Okay. Well, alarm, whatever. Okay, it's annoying. Okay, so the trick is always fill shells. All right, so we went through then this question where we had beryllium and fluorine. And if you do the electron configuration for beryllium, you find that beryllium has 2 electrons in the outermost orbital. So what you have to do is snatch those 2 electrons away. If you're reacting with fluorine, fluorine only has 1 space. So you're going to have 2 fluorine atoms that are involved in this reaction, and you actually form beryllium difluoride, 2 fluorines, okay, BeF2. All right, so the ionic bond then is formed by producing ions, charged atoms. The charged atoms have opposite charges, and so they attract to each other and stick. It's not a terribly strong bond. It's easily broken by water, for example. A much stronger bond is the covalent bond. For a lot of the stuff that we look at, covalent bonds are going to be the most important bond that we consider. Carbon, for example, forms exclusively covalent bonds. Right? It doesn't form ionic bonds. Right? They are a sharing of a pair of electrons. In the ideal covalent situation, the pair is shared equally, okay, between the 2 atoms participating in the bond. That's not always the case, though. Sometimes they are unequally shared, and that has some specific consequences that we'll talk about. Okay. So the electrons are spending time around both of the nuclei of the atoms, and that's what maintains the bond. That's what keeps the atoms in close proximity. You can form double covalent bonds. You can even form triple covalent bonds. It just depends on the number of electrons that are being shared. There is no way to form quadruple covalent bonds, though. And the reason is because of the bond angles. There's too much stress. You can't get the electrons close enough to each other to be able to be shared. But I'll show you examples of double and triple covalent bonds because they're fairly common, especially with carbon chemistry. All right, so as I said, sometimes the sharing is not equal. Okay? The electrons spend more time around one of the atoms than the other atom. That's a polar covalent bond. And what happens there is you get slight charges in the atoms in the molecule. The reason is that, for example, if an electron is spending more time around one nucleus than the other nucleus, that atom then picks up a slight negative charge. Some of the time it's going to be negatively charged, and some of the time it's not, depending on when that electron is around it. So we measure that as a slight negative charge. The atoms that don't have the electron around them as much as a result, have a slight positive charge because the nucleus charge is showing through. The charge of the protons is showing through. And so we have slight negative and positive charges. Those can attract. They're even weaker than an ionic bond, but they are if you have a lot of them, they can be very strong when you sum them all together. Okay. So here's some examples of covalent bonds that we can look at. The simplest one up there is the formation of a covalent bond between two hydrogen atoms. You remember hydrogen has one proton and one electron, and so what we see here up at the top of this figure is a sharing of those two electrons. Again, what we're doing is we're filling shells. Okay? Right? The lowermost shell can hold at most 2 electrons. Well, what we've got is basically 2 electrons. As long as we share between the two atoms, they both have filled shells. So our rule of filling shells still applies here. Right? So that's an equal sharing. The double bond that's shown here between these oxygen atoms is a sharing of 2 pairs. Okay, so there's an upper pair and a lower pair here. Again, we've filled the shells because we've got 8 electrons total in the outermost shell for each of these atoms. The sharing is still equal, mostly because those oxygen atoms are the same size. If they were radically different sizes, then there would probably be an unequal sharing. The larger of the 2 atoms would be sort of yanking those electrons away or pulling them away. Okay? Carbon always forms 4 bonds. The reason is because it has 4 unpaired slots in its outermost orbital. Okay, so it can form 4 bonds. That can be any combination of single, double, triple bonds. You could have a triple bond and a single. You could have 2 doubles, that sort of thing. Here, all we've done is we've taken carbon and reacted it with hydrogen, and each of those hydrogens forms 1 paired sharing of electrons with the carbon. So you end up having 4 hydrogen atoms arranged around this carbon atom. We've successfully filled the outermost shells of each of these atoms in that manner. Right? Methane is natural gas. Carbon can form double and triple bonds, and so can nitrogen. Right? So I ask you to think about that. Why is it that carbon and nitrogen can form triple bonds, but oxygen can't? The reason has to do with the number of unpaired slots that are available. Okay? Carbon has 4. So it could form a triple bond with 3 of those slots. And nitrogen has 3 slots available, so it could form a triple bond with its 3 slots. Oxygen only has 2 slots open, though. Okay? So it can only form, at most, double bonds. It can't form triple bonds. All right, now in all of these examples, the first 3 examples, those are all equal sharing. It's an equal partnership. You won't find a charge on these molecules. The 4th one is much different. Water forms an unequal partnership between the oxygen and its single-bonded hydrogens associated with it. Okay? The reason primarily is because of the size of the oxygen. Oxygen is so large that it's able to, in a sense, pull the electrons towards itself rather than sharing them equally. The result is that the oxygen picks up a slight negative charge, and the hydrogens pick up a slight positive charge. Okay, because of that unequal sharing, a polar covalent bond is not as strong as a equal covalent bond, or just covalent bond. All right? So it's much easier to break that polar covalent bond than it is to break a regular covalent bond. All right, this is a ball and stick model of methane. That's one of the molecules you saw in the previous figure. It's a carbon atom with 4 hydrogens. And the thing I want you to look at especially is that these bonds are not coming straight out of the carbon atom. I mean, in reality, of course, you don't have these little sticks there. You'd have the hydrogen, for example, very close to the carbon, and you'd have a cloud of electrons around the two. Okay? But the bond angle is at 45 degrees, and what that does is that puts some constraints on the three-dimensional shape of double and triple bonds. Single bonds are at 45 degrees. If you form a double bond, the second bond is stretched because of the bond angle. So that one's a little bit weaker. A triple bond is even weaker than that. There's a lot of stress placed on that triple bond. All right, so it is easy to break a triple bond. It is less easy to break a double bond, and it is very difficult to break a single bond, a single covalent bond. All right, so a single covalent bond is the strongest of the bonds that we talk about. This bond angle also sort of dictates the structure of carbon chains, which is really what we're going to be looking at in large measure when we look at biologically important molecules. Long chains of carbons, nitrogens, oxygens, and that sort of thing. Okay, so what you end up seeing is that those carbons are arranged in 45-degree angles to each other. Okay. So let's see if you remember which of these, or can figure out which of these is strongest and weakest. So what you need to do is just rank those in the order of the strongest to the weakest. Okay, if you remember, I said that ionic bonds are the weakest of the bonds that we'll talk about, except for the special hydrogen bond. And covalent are the strongest. So you know that your answer is going to have covalent in the front and ionic in the back. All right, well, the only other bond we've talked about is a polar covalent bond, so that's sort of sandwiched in the middle, which means that the answer is A. Okay? Ionic bonds are very easily broken. Covalent bonds are very difficult to break unless they're double or triple bonds. And polar covalent bonds are sort of in between the two. It's fairly easy to break a polar bond, but it's not as easy to break as an ionic bond. Because an ionic bond is, after all, just a charge interaction. That's all it is. The polar covalent bond is still a sharing of electrons, and so it's stronger. Okay, so that's the intermediate one of the three. Okay, your book goes on to talk a little bit about water chemistry, and it's an important topic. Water has some really unique properties that make it an especially valuable substance when you're trying to consider how life arises and how life works. Water's chemistry and properties are properties that very few other substances have. Okay? It really has to do with the fact that it forms polar covalent bonds, and almost everything extends from those properties of those polar covalent bonds. All right? So that's what's important in the water molecule, the polar covalent bonds. All right, here's a water molecule. As I said, the polar unequal sharing of electrons produces an oxygen atom in the water molecule that has a slight negative charge, and it will attract positive charges. The hydrogens, because the electrons are spending less time around those nuclei, will have a slight positive charge because the charge of the protons in the nucleus is showing through. All right? So those positive charges then will attract negative charges. What this means is that, for example, water molecules attract each other. Right? Only slightly, not as strong as a full charge, but they still attract. Your book doesn't do this, but in other books, they're often symbolized, these charges are often symbolized as a delta plus and a delta minus. This is a lowercase Greek letter delta. All right, so we use delta plus and delta minus to indicate a partial charge rather than a full charge. You'll see me do that sometimes in class, so you probably ought to be aware of what that means. All right, so we have charges on these water molecules. What does that do? Well, what it does is it causes water molecules to attract each other. And they form a really interesting bond called a hydrogen bond. It's a weak attraction between a hydrogen and a negatively charged atom in another molecule. In this case, other water molecules. Right? These interactions are transient because the bonds are weak. Right? A hydrogen bond is very easy to break. It's just a partial charge interaction. Molecules in liquid water are moving fast enough that these interactions break and reform all the time. Okay? So the plus and minus charges stick together, and then because of the movement of the molecules, they dissociate, that bond breaks, and other hydrogen bonds are formed. Okay? But when you cool water, those molecules are moving less and less and less. I mean, that's really a manifestation of heat energy. What is heat energy? Well, it's molecules moving faster. When you heat water to form steam, all you're doing is making those molecules move faster and faster, to the point where they break those hydrogen bonds, and the hydrogen bonds don't reform, in the case of water, and the molecules dissipate away. All right, so if you cool water, then the hydrogen bonds are more stable. They last longer. And that's going to be really important for some of the properties of water. All right, so what are some of those interesting properties? All right, well, one of those properties is the fact that water has a surface tension. It sort of has a skin on the top of it. And that skin is formed by those hydrogen bonds in the water molecules interacting with each other. That skin is strong enough that if an insect, for example, distributes its weight evenly over the top of that tension, surface tension, it can actually walk on the top of the water. Right? That's what these water striders do. If you look really carefully, you might see that there's a whole bunch of really fine hairs on the surface of this water strider's leg. What those hairs do is they distribute the water strider's weight evenly. Okay, it's the same kind of idea as when you use snowshoes on the snow. Okay, if you use the snowshoes, you're distributing your weight more evenly, you don't sink in. Whereas if you don't use the snowshoes, all your weight is on a small area of the snow and you sink in. Same thing with this critter. If it didn't have those hairs on its legs, it would sink. Right? Fall right in the water. But since it distributes its weight more evenly, it's able to walk on those hydrogen bonds. All right? So water has surface tension. Surface tension is important for another reason. It allows for what we call capillary action. If you put water in a very thin tube, that water spontaneously rises in the tube. Okay? The reason for that is, again, the surface tension. It's as if those hydrogen bonds are causing the water to go upwards in big clumps up that tube. Trees and other plants take advantage of this to great effect. I mean, a 200-foot tall sequoia is able to pull water all the way up to the top of the tree simply because of this capillary action. Water evaporates from the leaves. That creates a vacuum that starts to suck water up from the conductive tissue in the trunk. And capillary action allows that water to be sucked up back into the leaves. Right? So trees and other plants are depending on that capillary action, that surface tension, in order to obtain water. And that's why they can grow so big. Right? Another thing that water does is when it evaporates, it carries heat with it. Because of the hydrogen bonds in water, when you put heat into water, it absorbs a lot of that heat. So water heats up really slowly. But when it does heat up, it retains that heat very well. Okay? And this is particularly important for organisms that are aquatic, that live in the water. Organisms in a lake in a very cold winter are still reasonably warm in that lake because the water is still retaining heat that it absorbed, say, during the summer. Okay? And it doesn't get rid of that heat very quickly. But when water does evaporate, it carries heat away with it. All right? So as I said, heat's the energy associated with movement of molecules. The faster molecules move, the more heat that's associated with them, the more heat energy they've absorbed. Okay? So it takes more heat to vaporize water. And as a result, when water molecules leave that remaining liquid, when they evaporate away from it, they carry heat away from it. And the remaining liquid cools. This is why you sweat. Okay, it's your body's way of getting rid of that excess heat. The water is carrying it away as that sweat evaporates. Okay, so we use that to good effect. Right? This also keeps water liquid for a far longer period of time than other similar molecules would stay in a liquid state, because it can absorb an awful lot of heat. It gets rid of heat very slowly, so it stays liquid much longer. Okay? Now, everybody's aware that ice floats, but they might not have thought why it floats. Usually solids are denser than their liquid form. Right? Denser meaning, you can think of dense as being more molecules per unit volume. Water is really, really interesting because a given volume of ice has fewer molecules in it than a given volume of liquid water. All right? So ice is less dense than liquid water. Now, the reason for this is that in liquid water, the hydrogen bonds are constantly breaking and reforming all the time. Those atoms, or those molecules, are very close together. They're bumping into each other, they're forming those hydrogen bonds, they're breaking away constantly. As you slow them down, as you remove heat from that system, and as those molecules start to slow down, those bonds last for a longer and longer period of time, to the point at which they become stable. They don't break. When they become stable, they establish a regular distance between water molecules, which is greater than the distance established when the water is liquid. That's why you have fewer molecules of water in a given volume of ice than in the same volume of liquid water, because the hydrogen bonds are longer. All right? I mean, this is extremely important for aquatic ecosystems. You get this sheet of ice across the top of a pond and the bottom remains liquid. The ice is a great insulator, too. It keeps that heat in that lake rather than letting the heat dissipate out into the air. Okay? So it's critically important. That ice is also pure water. Okay? The impurities get all filtered out as the water freezes. So icebergs that are formed from salt water are actually fresh water. Okay? So the reason for that is that ions that are dissolved into this water, they're forced out as this crystal structure is produced. There's no room for them. So they just get forced out of it. Okay? Because water is polar and it has slight charges, it's really good at breaking ionic bonds. So if you drop a crystal of salt, sodium chloride, in water, then it's going to break down very, very quickly. The reason is because you get charge interactions between the chlorine ions and the sodium ions in the salt crystal. Okay, those are breaking away as they get surrounded by water molecules. Right, so that's really what's happening. Okay, the water molecules surround the ions. You end up getting those ions pulled away from the salt crystal, and eventually that crystal dissolves completely. Because water is polar and not fully charged, it also interacts pretty well with some less polar things. Alcohol, for example, which has oxygen and a hydrogen on it, can form hydrogen bonds with water, and so it will dissolve in water. All right, so any polar or ionic substance will usually dissolve in water. That's important because water then serves as a medium for chemical reactions to occur. Right? If you don't have the water, then it's much harder to bring molecules into close proximity so that they can actually react with each other. Water molecules themselves can break and reform spontaneously. You remember I said that the ionic bond is, or the polar covalent bond is a weak bond. All right? It's fairly easy to break. In fact, it breaks spontaneously in water molecules. And what happens is you form a hydrogen ion, which is basically a free proton, and a hydroxyl, or an OH minus ion, oxygen and hydrogen, that's got an extra electron, so it's negatively charged. All right, so that happens in water spontaneously. Okay. Well, let's test your understanding here. Which of the following substances will dissolve the fastest or the most or the easiest in water? What you're going to have to do to answer this question is draw on some stuff we've talked about, for the last half an hour. What kind of bonds are formed in these molecules? Are they charged? Are they not charged? Are they polar? Are they nonpolar? Okay, all of those things are going to come into play here. So take a little bit of time and see if you can figure this out. It should actually be fairly obvious. Okay, let's see if we can find a consensus here. How many people say A? Anybody? Good. Okay, the reason you don't there is because methane is just a carbon and 4 hydrogens. Those are nice, regular covalent bonds. They're not polar. It's an equal sharing, so that stuff's not going to dissolve very easily in water. How many people say B? Okay, good. Again, those are regular polar or regular covalent bonds. They are not polar. Interestingly, this has some constraints on aquatic life. If they need oxygen, they have to be super efficient at getting getting it out of the water because oxygen dissolves in water only at a very low rate. Okay? There's only 10% as much oxygen dissolved in water as you'd find in air, and air has about roughly 20% oxygen. All right? So water might have 2% oxygen in it. So aquatic organisms have to be really good at pulling oxygen out of that water. How many people say C? Okay, good, majority. So what you did is you probably looked at this and said, oh, well, magnesium chloride, it's a salt. It's a magnesium and 2 chlorines. And if you're following the rules for ionic bonds, magnesium is in that second leftmost column on the periodic table. Right? Chlorine is on the next to last. And that's clearly a case where you're going to form ionic bonds. All right, so magnesium chloride has ionic bonds, and so it dissolves very readily in water. Ethane would not, because it is what we call a hydrocarbon. It's just carbons and hydrogens. And again, those are covalent bonds, and they are equal sharing. Carbon tetrachloride, the same thing. Now, the only confusion you might have had was between C and E. Carbon tetrachloride, though, is not polar or ionic. Yeah, you've got chlorines in there, but they're bonding with a carbon. Carbon bonds are not polar. Okay? They're always regular covalent bonds. Right? And so that's why you would not want to choose answer E. Right? So answer C is the correct one. It's the only one up there that's ionic. Hope that wasn't an editorial comment. Trying the best I can. All right, so another property of watery solutions that we talk about is pH. If you're curious, that means pontus hydrogeni. It's a Latin, derived from a Latin term. It refers to the concentration of hydrogen and hydroxyl ions in a watery solution. Okay, or aqueous solution. pH scale is logarithmic. And so what we have is a scale that sort of starts in the middle at 7 and goes down and then up. And both of those have opposite meanings. Okay, a low pH means a high hydrogen ion concentration because this is an inverse log relationship. All right? So if we look at this table, numbers lower than 7 are more acidic. That is, they have more hydrogen ions. That's the basic definition of an acid. Right? Lots of hydrogen ions. All right? So, tomato juice is around pH 4, grapefruit juice 3, lemon juice 2. Mountain Dew is somewhere in the middle between 3 and 4. Okay? Yeah. That's okay. I mean, your stomach can handle it. It's down around 2. If you have a high pH, that means a low hydrogen ion concentration, or alternatively, a high hydroxyl ion concentration. We call those basic solutions. So as you go higher than 7, you're getting more and more basic, where the hydroxyls outnumber the hydrogens. Okay, so here's seawater, milk of magnesia, ammonia is down around 11.5 or so, bleach at 12.5, oven cleaner at 13.5. Okay, and strongly basic substances are just as dangerous as strongly acidic substances. Okay, antacids are somewhere between 9 and 11 typically. Not usually much close to 11, somewhere around 9, maybe 10.2, 10.3, right, depending on what you're taking. All right, low pH means low hydroxyl. All right, so there's an inverse relationship. We said that low pH is high hydrogen ion concentration, so low pH is low hydroxyl. The hydrogens outnumber the hydroxyls. And conversely, with a high pH, the hydroxyls outnumber the hydrogens in those kinds of solutions. All right, so low pH is an acid, and high. What? There's some, but it's around pH 6, so it's not dramatic. Most of what you're thinking of is sort of acidic is absorbed by the nitrogen groups that are in the urine that you're getting rid of. Yeah. Okay, 7.0 is neutral, right? For example, distilled water has a pH of 7.0, and what that means is that you have an equal concentration at any given time of hydrogen ions and hydroxyl ions. Okay. The pH of water matters. All right, your book has a section on acid rain. I know a lot of people poo-poo acid rain, but I'm telling you, acid rain's real. It's been measured. We can see the dramatic effects of acid precipitation, rain and snow. The problem here is that when you get lots of sulfur in the atmosphere and lots of nitrogen-oxygen compounds like nitrogen oxide, sulfur dioxide, those sorts of things. When they mix with water, they form things like sulfuric acid and nitric acid. And that lowers the pH of the precipitation. So you're basically getting acid precipitation from those atmospheric pollutants. In industrialized areas, it can have a very dramatic effect. This is a picture of a statue that was taken in 1908. This is the same statue in 1968. You can't hardly tell what it looks like. And that's just from erosion by acid precipitation. Okay. Europe's had a big problem with this because Europe industrialized dramatically and heavily and produced an awful lot of acid precipitation. Okay, well, okay, so our structures are affected. You know, as you say, big deal. Well, we can just rebuild those. Yeah, but the biological world is affected as well. All right? These are trees that have been burned by acid precipitation. They're dead. Acid precipitation lowers the pH of waterways, lakes, streams, rivers, ponds. Right? When you lower the pH of these systems, these aquatic systems, you affect that ecosystem. You strongly affect the ability for those organisms to live in that ecosystem. Right? Where is the nitrogen and sulfur coming from? Well, it's basically coming from coal-fired plants and from gasoline engines. Okay? If you go up a hill, if you're going up, say, Ladd Canyon or outside, you're going west towards Pendleton, you're going up that hill, you might smell a sulfury smell, sort of like rotten eggs. It's the sulfur burning out of the gasoline that we get here. Our gasoline is high sulfur gasoline. And as a result, you burn that out and you produce sulfur oxides, sulfur dioxide being a typical one. And that sulfur dioxide gets in the air. It mixes with the precipitation or the water in the air, and you produce sulfuric acid, which then rains or snows down. Okay. So, you know, there's two things that are happening here. We're getting acid precipitation from these coal-fired plants and from gasoline engines, and we're pumping just tons of carbon dioxide into the atmosphere. And yes, that has an effect. Okay? Carbon dioxide is a greenhouse gas, and what that means is that carbon dioxide allows solar energy to come in, but it doesn't let it get out. Right? Solar radiation, heat energy, bounces off of carbon dioxide in the atmosphere and comes back down. So we're constantly receiving energy from the sun. If it can't escape, then it stays here, and that energy warms us up. Right? The amount of carbon dioxide that we're releasing is more than can be removed by the plants that take carbon dioxide and make sugars out of them. Okay, so we're slowly building up carbon dioxide, and that's having an effect. All right, last thing here. Chemical reactions. We'll talk a lot more about chemical reactions, but I just want to introduce the idea here. It's a process leading to a chemical change in a particular molecule. Okay, this is a very complicated molecule. Lots of double bonds in there. The way this is being represented in this figure is that the double lines between these carbons, those are double bonds. Single lines are single bonds. Okay? Some of these bonds we aren't showing. We've got a CH3 here. You should take that to mean that that's a carbon with 3 hydrogens bonded, covalently bonded to it. But we're just not showing all the bonds. This would get ridiculous if we tried. Okay? It's not a change in the physical state. A change in the physical state would be a change from solid to liquid to gas. Okay? It's a real chemical change. We get a different chemical compound or molecule. On the left side of the equation are the reactants. That's what goes into the reaction. On the right side is what comes out of the reaction. Those are the products. Okay? The red arrow up in this figure shows the bond that's broken to produce the products. And the products here are vitamin A, made from beta-carotene. Okay, notice that the equation is balanced. Okay, chemical equations should always be balanced. And having said that, I'll hope that you'll do as I say and not as I do. I'm very bad at balancing equations. I usually don't do it very much. And in biology, I'm not terribly worried about it. But you should typically try to think about what's going in and what's going out and try to figure out, how many oxygens do I need to put in here so that I get the same number of oxygens out on the other side. All right, so we have on the left side the beta-carotene, an oxygen molecule, 4 hydrogen, those will be hydrogen ions. And what comes out is 2 vitamin A's. Those oxygens and hydrogens are getting picked up here at the end to fill up the bonds that are broken when this double bond is broken right here. Okay? That's why those oxygens and hydrogens are going in. All right, so we'll talk in Chapter 5 much more about chemical reactions, but I just wanted to introduce the term to you now. And since that's the end of the slideshow, we'll stop there and we'll start Chapter 3 on Friday.